All right, let's look at this last example. Example C, we've got a function here, f of x, equal to x squared minus 4 divided by x plus 1. Now, as we go ahead and factor, we notice we have a quadratic degree 2 polynomial. We have a difference of squares, x squared minus 2 squared, so we can easily factor it x minus 2, x plus 2. And as we do that, we see there's no common factors. With that said, are there any holes? No holes in this graph. All right, and why? Again, because there's no common factors. So the common factors tie into your holes. If you have a common factor, you're going to find the zeros of that common factor, and then that'll be location of your hole. Now we do have a vertical asymptote. So as we move on, getting more characteristics with this graph of this rational function, we're going to have a vertical line that's going to shape our graph. And remember, how do we find that? We're going to look at the zeros of the remaining denominator factors after you factored your function and reduced it. Of course, there's only one factor, that's x plus 1. We know that equals 0 when x equals negative 1. So that means we have a vertical asymptote at negative 1 on the x-axis. So again, our graph will go vertical. It's an undefined value, no holes. Let's go ahead and write in the domain. We already know what domain will be. All the real number values of x, every real number except negative 1, the only undefined value. So x less than negative 1 or x greater than negative 1. Let's move on. Let's add to information. Let's look at if there's a horizontal asymptote with this graph. And remember, to find out whether or not we have a horizontal asymptote, we're going to compare the degrees of the two polynomials, and we're dividing. Now we'll let n be the numerator degree. Remember, this is a quadratic, so we have a degree 2 polynomial in the numerator, and our denominator is a linear, a degree 1 polynomial. And with that, we have n being greater than m. Well, this is the one case in which there is no horizontal asymptote. So no, there is not a horizontal asymptote. Nowhere on this graph will it flatten out horizontally. Now that leads to our third possibility. When we do not have a horizontal asymptote, it's possible to have a slant, or some people refer to it as a oblique asymptote, which again is a slanted line that will shape our graph, and it occurs if the degree of the numerator is exactly 1 greater than the degree of the denominator. So if n is 1 more than m, which it is in this case, in this problem we have that, right? N is equal to 2 and m is equal to 1. So that implies what? N is 1 greater than m. So that implies we do have an oblique or a slant asymptote, right? We have a slanted line that exists. Now, how do you find that slant asymptote? To find the slant asymptote, we're going to find the quotient from this polynomial function. We're going to divide. So we've done polynomial division. So let's divide. We can do long or synthetic in this example. But x plus 1 divides into x squared minus 4. And we'll put in the missing term. We're missing the x term. So we'll go ahead and place that in there. And as we divide, x divides in x squared exactly x times. Let's distribute. X times x is x squared. X times 1 is x. So we subtract to see what's left over. 0x minus x is negative x. Bring down the next term. What is our new dividend? This is a linear expression. First term in divisor. First term in dividend is a negative x. We know x divides in negative x exactly negative 1 time. Why? Because we know that negative 1 times x is negative x. Negative 1 times 1 is negative 1. As we subtract to see what's left over, we get a remainder. Right? These cancel. Negative 4 minus negative 1, that makes plus 1. That's negative 3 as a remainder. But what we were looking for was the quotient. There's the quotient, q of x. So y equals q of x. So what type of line is this? This is a line with a slope of 1 and a y-intercept of 0, -1. That's our oblique or slant asymptote. So we graph in that line, right, to help shape, again, this graph of this function. Now, how about the x and y intercepts? Again, you can find those points, right, if you want to find the x-intercept points. All right, let's go ahead and do that. Let's set our function equal to 0, and let's solve for x. So when is x squared minus 4 over x plus 1 equal to 0? Well, that implies when is x squared minus 4 equals 0, which is what? We know that's going to be x minus 2, x plus 2 equals 0, so that means x equal 2, or x equal -2. Remember, it's the zeros of your numerator. Remember, we factored it earlier, we could see that. So we'll have an x-intercept at -2, 0, and an x-intercept at 2, 0. So there's two x-intercept points. And we could add to it the y-intercept, which again would be what? Set our function and set x equals 0. So f of 0 equals what? So as we plug in 0, what do we get? We get 0 squared minus 4 over 0 plus 1, which is -4 over 1, which is -4. So we'll have a y-intercept at 0, -4. So there are characteristics, right, for this rational function. And again, you can use that information to get a sketch of this graph. And again, we said, talking about checking our graphs with our TI, this would be a good opportunity to do that. Let's get our calculator out. Let's take a look at this function on our TI, and let's see if we can see this information that we found. So let's go store this in y equal. So x squared minus 4, let's go put in x squared minus 4, divided by denominator of x plus 1, and we'll graph it. We can put it on a standard window. You can see this graph now. If you look at, let's put in here, we'll put it in a different color. Let's look at the graph of the slant asymptote that we found. So remember, we had a slant asymptote at x minus 1. So I want to show you this graph. As you see your graph, look at it slanting out. Right here you can see again it's approaching that line like a magnet pulling your graph to it. So it's going vertical there at -1, vertical asymptote, and slanting out at y equal x minus 1. And you can see that there with your grapher. Of course, the x-intercepts at 2 and -2, and y-intercept at -4. And again, all of that can be seen there, right? If you look at your table of values, you can see those intercepts, right? 2, 0. You can see again at -2, 0, and so forth. So again, I just wanted to show you that. And that's again a good way to check your information. But that's an example of a rational function with an oblique asymptote, which we have not seen an example of. So oblique asymptote exists if the degree of the numerator is exactly 1 more than the denominator. And how do we find it? We're going to divide, right? We take our given function, f of x, and we do the division and find the quotient. So you see, again, the characteristics of rational graphs.